So let's talk about one of the biggest questions in all of computing. How do you get thousands or heck, even millions of processors to all work together perfectly on one single problem? I mean, this challenge is right at the heart of pretty much all modern technology. So here's what we're going to do in this explainer. We'll start by imagining the perfect theoretical machine. Then we're going to see exactly why you can't actually build it in the real world. And from there, we'll dive into the brilliant practical solutions that engineers have come up with to make it all work. All right, let's get into it. All right, so let's just dream for a second. What would the absolute perfect parallel computer look like if we had no physical limits, no budget constraints, nothing holding us back? What would we build? Well, computer scientists have a name for this ideal machine, the Parallel Random Access Machine, or PRAM. The best way to think about it is like this. Imagine a giant library with an infinite number of books. A PRAM is that library, but where every single person can grab any book they want from any shelf at the exact same time, with absolutely zero delay. Instant access for everyone, all at once. So yeah, this is basically the perfect wish list. You've got a whole bunch of processors, this huge shared pool of memory, and this is the critical part, every single processor can get to any piece of that memory instantly. It's the dream, right? Total, frictionless access to information for every single part of the machine. It sounds incredible. A computer that literally never has to wait for data. But, as you might have guessed, this dream machine runs smack into a very hard, very real wall. And here it is, the cold, hard truth. You just cannot build a true PRAM in the real world. It's a fantastic idea, a really useful tool for thinking about algorithms, but it will never, ever sit on your desk. So the big question is, why not? This slide just perfectly nails the problem. It's the wiring. It's always the wiring. To connect every processor to every single piece of memory instantly, you need this enormous grid of switches. But the number of connections you need, it grows exponentially. That means adding just a couple more processors doesn't add a couple more wires, it adds a mountain of them. For any system big enough to be useful, you'd end up with a machine that's physically impossible to build and would cost more than, I don't know, the entire planet's economy. Okay, so if the perfect dream machine is a no-go, how do we solve this in the real world? Well, engineers came up with a really clever, practical solution to connect all those processors without, breaking the laws of physics or bankrupting the world. The answer is something called an interconnection network. It's not the sexiest name, I'll admit, but it is the absolute communications backbone, the central nervous system of every parallel computer that exists today. It's the fabric of switches and wires that actually carries all the data where it needs to go. And they basically come in two main flavors. On one side, you've got static networks. Think of these like a permanent system of roads connecting cities. The links are fixed, they don't change. On the other side, you have dynamic networks. These are more like an old-school telephone switchboard, where an operator could physically create a temporary connection between any two people who wanted to talk. Okay, this is where it gets really cool. Since we can't build one single perfect network, engineers developed a whole catalog of different designs, or topologies. Let's take a quick tour of the most common ones, because each has its own unique pros and cons. First up, we have one of the simplest and oldest designs out there, the bus. Think of a bus network as a single-lane road for an entire city. It is incredibly simple and cheap to build, which is a big plus. But as you can probably guess, if every single car needs to use that one road, you get an insane traffic jam. That shared bus becomes a huge performance bottleneck because only one conversation can happen at any given moment. All right, so now let's swing to the complete opposite end of the spectrum with something called the crossbar. A crossbar is like having a dedicated private road from every house to every other house in the city. It's unbelievably fast and efficient. We call it non-blocking because different messages don't interfere with each other. But the catch? Oh, there's a big catch. The cost is just astronomical. It grows as the square of the number of processors, making it completely unaffordable for large systems. Okay, so between those two extremes, we find a really popular and practical middle ground, the mesh topology. With a mesh, you just arrange all your processors in a grid, kind of like a checkerboard, and each one is only connected to its immediate neighbors. If you need to send a message to a processor far away, the data just hops from neighbor to neighbor until it gets there. It's like passing a note in class. It strikes this really great balance between cost and performance, and that's why it's such a popular design. Now for something a little more complex, a little more mind-bending, but often way more efficient, the hypercube. A hypercube is just a super clever design. Think of it like a mesh, but in more dimensions. The truly amazing thing is how it keeps communication paths short. The number of hops a message has to take grows logarithmically. Now, what that means in plain English is that even if you double the number of processors in your system, you only add one extra hop to the longest possible journey. That makes it an incredibly efficient way to connect a very large system. So you've got this whole menu of options, from the simple bus to the complex hypercube. How on earth does an engineer choose? Well, it all comes down to a few key numbers and what we call the art of the trade-off. This table just lays out the whole challenge beautifully. Look at the extremes. On the right, a completely connected network, like our crossbar, has the best performance. A diameter of 1 means instant connections, a huge bisection width means massive bandwidth, but its cost is through the roof. Then look all the way to the left. A simple linear array is super cheap, but its performance is just awful. And right there in the middle, that's where you see the mesh and the hypercube, sitting in that design sweet spot. And that brings us to the most important takeaway of this whole thing, summed up perfectly by this quote right here. There is no single best network, not one. Every single design is a compromise. Computer architecture isn't about just finding the fastest possible solution. It's about finding the right solution that fits within a set of real-world constraints. It's this constant juggling act. Every single design choice is a deliberate trade-off. Engineers are always balancing these three critical factors: speed, which is how long it takes a message to make its longest journey; bandwidth, how much data you can move at once; and, of course, the actual cost to build the thing. The goal is always to find that perfect balance for a specific job, whether it's modeling the weather, doing scientific research, or just powering your favorite social media app. So that leaves us with a final thought. There's this invisible architecture of choices and compromises behind every powerful computer system we rely on every day. The next time you use some complex online service and it feels totally instant, just take a second to appreciate the incredibly intricate web of trade-offs that engineers had to navigate to make it all possible. It's a constant dance between that dream of perfection and the reality of what we can actually build.